We have seen in the previous lesson that dehydration of tertiary alcohols is a facile process. It proceeds by the E1 mechanism. It's a well-behaved E1 mechanism. It takes place under relatively mild conditions. If you take a tertiary alcohol, react it with an acid as dilute as 20% sulfuric acid, and heat it up to 85 degrees, dehydration will go to completion. The question now is it possible to dehydrate a primary or a secondary alcohol? So let's look at some experimental evidence. If you take a primary alcohol such as ethanol and react it with 20% sulfuric acid at 85 degrees, it will do nothing. Even if you go to 90 degrees or 95 degrees, frequently when a reaction doesn't do anything, the answer is just to heat it up a little bit more and then maybe it will. No. You have to get all the way up to 180 degrees, and instead of using 20% sulfuric acid, you have to use concentrated sulfuric acid, 98% sulfuric acid. And then, and only then, you will see alkene product, namely ethylene. So heating something up to 180 degrees in concentrated sulfuric acid is what we chemists refer to as forcing conditions. Okay, this is something that does not really want to react, but if you beat on it hard enough, you can get it to do something. And what about secondary? I'm giving you a rather interesting example here. This molecule is 3,3-dimethyl-2-butanol, and you don't have to heat this one to 180 degrees. You only have to heat it to 160 degrees. And you don't actually have to use sulfuric acid for this reaction. This reaction will go in phosphoric acid, and concentrated phosphoric acid as an aqueous solution is 85% phosphoric acid. Pure 100% phosphoric acid is what we call orthophosphoric acid. That is actually a solid. But 85% phosphoric acid is the most concentrated aqueous solution that is, of course, a solution. So we get dehydration products out of this. We get two dehydration products, which you should be able to recognize as being a Zaitsev product. You have a tetrasubstituted alkene, and an anti-Zaitsev product, a 1,1-disubstituted alkene. But the conditions are still harsh, and if you look at these products really carefully and look at the starting material, you might think I made a mistake. These are actually not the dehydration products you would expect out of that particular starting material. So we have unusual products going on here, and we need to see if that gives us any clue into the mechanism. Okay, so these reactions go, but they're not happy about it. The question we need to answer is, are they going by the E1 mechanism or by the E2 mechanism? Neither mechanism is particularly attractive for a primary or secondary alcohol. Why is this? Well, the E1 mechanism would require a non-tertiary, non-resonance stabilized carbocation. And up until this lesson, we've been under the impression that such things do not exist. Whereas for the E2 mechanism, the paradigm that we've set up so far involves the E2 mechanism requiring a strong base, at least hydroxide or stronger. And under the acidic conditions that are required for a dehydration reaction, the strongest base available is either water or dihydrogen phosphate, both of which are way too weak to be a base in an E2 reaction from what we've seen up until this point. Okay, so we got to sort this out a little bit. The answer will actually be different for primary than it will be for secondary, and the primary case is a little bit simpler, so we'll consider that one first, even though those are the harsher conditions. So if you can get a primary alcohol to dehydrate, it's going to dehydrate by the E2 mechanism using water as a base. So step one of this mechanism is familiar. It's protonation of the alcohol to make a good leaving group. And then because it's an E2 reaction, everything else happens all in the same step. Okay, remember the E2 reaction of an alkyl halide was a one-step mechanism, but when we're using an alcohol as a starting material instead of an alkyl halide, we have to add one step to the beginning of the mechanism, which is proton transfer to the alcohol to make it a good leaving group. The elimination step now requires 3 arrows. You have 1 arrow going from the base to the beta hydrogen, removing the beta hydrogen. The second arrow has the electrons from the carbon-beta hydrogen bond, forming the carbon-carbon double bond, and the third arrow is kicking out water as the leaving group. So in this reaction, we generate a molecule of H3O+, we generate a molecule of water, as it is a dehydration reaction. And once again, just like in the E1 reaction that we looked at for a tertiary alcohol, when we start with sulfuric acid, we are actually generating a weaker acid, H3O+, than we did in the beginning. Now note that water is needed in this reaction as a reagent because it is the strongest base present. The water that is needed is regenerated at the end of the elimination step. So therefore, a catalytic amount of water is actually enough to make this reaction go. You may wonder where water is coming from if you're just taking ethanol and reacting it with sulfuric acid. But as I mentioned to you on the previous slide, concentrated sulfuric acid is 98% sulfuric acid and 2% water. So that's where the water that you need to get the reaction going is actually coming from. So the reaction basically has to pick its poison, right? Would it rather go E1 with a primary carbocation or E2 without a strong base? And in this case, it chooses E2 without a strong base because the primary carbocation without resonance stabilization is really and truly impossible. Now for the secondary alcohol, we need to determine the mechanism, once again, E1 or E2, and explain the unusual products. So the expected reaction of 3,3-dimethyl-2-butanol would be to give the terminal alkene shown. Okay, that would be 3,3-dimethyl-1-butene. But the observed products are 2,3-dimethyl-2-butene and 2,3-dimethyl-1-butene. Okay, so the methyls are at positions 2 and 3 rather than at positions 3 and 3. So that's suggesting that a methyl group moved, didn't it? Well, let's work our way through this reaction mechanistically. And in order to do that, I have to tell you that the unusual product is actually proof that this reaction is going through the E1 mechanism with a secondary carbocation. Okay, the secondary carbocation is not as bad as a primary carbocation. So when this reaction has to pick which poison it would prefer, it is choosing the E1 mechanism with a secondary carbocation rather than the E2 mechanism with water as a base. The other clue that the mechanism has to be different are the reaction conditions. If this reaction were going E2, the reaction conditions would need to be just as harsh as the primary case that we looked at on the last slide. You would need the same temperature and the same acid concentration, but the conditions are not as harsh. We're using an acid that's not as strong, in not as high a concentration, and at a lower temperature. So that should be implying also to you that a mechanism is different. So the first two steps of this mechanism are very familiar. I'm actually combining them both onto the same set of arrows. This is a perfectly acceptable way of doing it. I know in my previous lessons when I went through a mechanism, I wrote out step 1, step 2, step 3, etc. separately, with each step getting its own chance to shine. But it is okay to link steps, and it's actually okay to not even label everything as step 1, step 2. What is not okay is to do 2 steps at once. You have to include every intermediate that is present in this mechanism. So step 1 involves protonation of the alcohol to make it a good leaving group, and we have the intermediate with the protonated alcohol. This then cleaves the carbon-oxygen bond, kicking off water as a leaving group and leaving the secondary carbocation. But, as I said, in order to get to the observed product, there has to be a structural change at some point. One of the methyl groups has to move, and it is at this point that the methyl group moves. This is referred to as a carbo-cation rearrangement, and that will be the subject of our next lesson.